Let's try the same thing that we did with e to the x using sine of x. This tends to go a little quicker because sine has cyclical derivatives and sine of 0 is 0, so you're going to see a lot of terms go away. So let's just note that f of x is equal to sine of x, f prime of x equals cosine, f double prime would be negative sine, f triple prime would be negative cosine, and the fourth derivative is going to be sine again. Alright, and therefore f of 0 is equal to 0, f prime of 0 is equal to 1, f double prime of 0 is equal to 0, f triple prime of 0 is equal to negative 1, and the fourth derivative at 0 is equal to 0. So now I've got that information, and we can use the info we did last time. We found that, I'm just going to jot these down quickly. So p of x, or p prime of x rather, p prime of x we found to be a1 plus 2a2 plus 3a3 x squared plus 4a4 x cubed. The second derivative would just be oops, I missed an x there, right? 2a2x. The second derivative would be 2a2 plus 6a3x plus 12a4 x squared. The third derivative would just be 6a sub 3 plus 24a sub 4x, and then the fourth derivative would be 24a sub 4. And therefore we can write that p of 0 we know is a1, p prime of 0 we know is p of 0 is a0, p prime of 0 is a1, p double prime of 0 is 2a2, p triple prime of 0 is equal to 6a3, and p, and the fourth derivative evaluated at 0 gives you 24 a sub 4. So once again, we do this matching game. So we want p of 0 to equal f of 0. So that means that we want p of 0, which is a naught, to equal f of 0, which is 0. P prime of 0 we want to equal f prime of 0. We want all these things to agree. So p prime of 0 is a1. We want that to equal f prime of 0, which is 1. P double prime of 0 was 2a2, and we want that to equal f double prime, which is 0. P triple prime of 0 is 6a3, which we want to equal f triple prime of 0, which is negative 1. And the fourth derivative was 24a sub 4, which means that we want that to become 0. So, putting that all together, we're going to get our Taylor series for sine. So we've got that we would want p of x, p sub 4 of x to be, well, a naught is 0, a1 we found to be 1, a2 is going to be 0. I guess I didn't write it up here, but a2 would be 0. so 0 x squared, plus a3, which is negative 1/6. And then a4, which we found to be 0. And so there is the fourth, which is called the fourth degree Taylor polynomial for sine of x, and this is centered at x equals 0 because we made everything agree at 0. And as before, with e to the x, just things to point out. One is that technically, if I wrote in everything, this is really 0 over 24. This is really 0 over 2, if you go back up to these guys here. This is really 1 over 1, and this is really 0 over 1. And again, this, if you track where this 0 came from, right here for instance, that 0 is this 0, which is just the fourth derivative of f at 0. And similarly, this negative 1 here is just the third derivative of f at 0. The second derivative of f at 0. The first derivative of f at 0. And that's just f of 0. And, as before, this 24 is our 4 factorial, 3 factorial, 2 factorial, 1 factorial, and 0 factorial. So, as with e to the x, using sine, we get the same pattern that emerges. And so, it's independent of the function. The pattern is independent of the function. It's always going to involve the derivatives of the function at a particular x value, in this case 0, and then those progressive factorials. So I'll later put down e to the x and sine of x. Cosine of x is another one that comes up. In terms of those are three of the ones that you're going to end up memorizing. And so if I said what's the Taylor series for sine of x centered at x equals 0, or the fourth degree Taylor polynomial for sine of x at x equals 0, you would write down this above. You would say, okay, and we wouldn't write the 0 in, but you would say that's just going to be x, and then the next guy that shows up is minus x cubed over 3 factorial. And if you kind of anticipate what the next one's going to be, you can imagine that since the fourth degree term goes away, it's going to be a fifth degree. And the signs, you'll notice, are alternating in terms of what's remaining, right? So this is a plus, that's a minus. So the next one's going to be plus x to the fifth. And actually, I'm going to get rid of the subscript. We'll just say, right, etc. So, so each function sort of has its own particular Taylor polynomial. This is the one for sine. And I'm going to go look at Desmos in a second to show you that when you graph these polynomials and look at them in relation to sine of x, the further out you go in terms of degree of the polynomial, the better these approximations are to the function sine of x, but only near x equals 0. So now I have a Desmos graph. You can see here that I've got in red sine of x, and I've got in blue, I've got the fifth degree Taylor polynomial for sine of x. And what you should notice is just how well our polynomial is conforming to sine of x, but only around x equals 0. You can see as you move further and further away from x equals 0, then the polynomial and sine of x start to split and go in different directions. But just notice, looking at the tables, look at that the values of sine at 0 and the value of the polynomial at 0. Those agree. When you move slightly outside that range, or that value, for instance at x equals 1, they differ, but they don't differ by a whole lot. I mean, 1 is a pretty big distance, but they only differ by, it looks like, not even till you get to the 10,000th place. So that's pretty good. That means our polynomial does a really good job of approximating sine of x near x equals 0. Now if you want to do an even better job, you could just expand, add more terms. So this is the fifth degree, but you could go ahead and add the next term. We'll do that. So that would be minus, you can probably anticipate, x to the 7th divided by 7 factorial. You can see it's even, maybe it's tough to see visually because they're getting so good, but it does an even better job of approximating if you just kind of look at the values here. So the point is that these Taylor polynomials are built based on a function using the function's derivatives at a particular x value. In this case, the value is 0. All right, and so we're going to formalize this in the next video. But for now, the main thing to understand is that we can use polynomials to approximate functions, and we are building towards a recipe for how to make those polynomials, and they involve derivatives of the function.